Alright, part two. Let's see if we can get everything back in order. Okay, screen's back on. Let's see if it's working. Oh, there we go. Good. Everything's in good order. Okay, where we left off is we were defining, so because there were no y's in that equation, and our whole depth of our volume of our one slice of water in that particular tank that we see up above, it has to be the thicknesses in terms of y, just because of the way they set it, because they said you're set up at the x-axis, or where the origin's at the center of the bottom of the barrel, and then, you know, basically positive y-axis upward from there. That really orients your box, or I should say your trough. Okay, so here is the drawing that gives you a relationship between x and y. It may not look like it, but from this little drawing, we can actually write a ratio. It often comes down to this writing a proportional relationship. And when it comes, so if I look more carefully, get another highlighter color. Let's go green. That little triangle right there that I just put in green, it has sides that are proportional. If you put a segment through a right triangle like that, there's this ratio where 0.75, the big base of that green triangle, to the little base x, that relationship is the same as the big height, which we know is 3, all the way down, you know, top to bottom. That's 3 from top to bottom, is 2. So that was big base to x is that, maybe I should do it a different way. Yeah, let's back it up. That's probably a confusing way to look at it. Hang on, let me try it another way. I got options. Okay. You could do it a couple ways. You could do like 0.75 is to 3, so it's like the big base with 3, it's big height across here. As x, it would be the same relation as little base is to little height, y, which is the little one on the side there. That's one proportion you could write. In fact, the crazy thing about proportions is you can write them a lot of different ways. Ultimately, what has to be the same, though, is these cross products have to be the same. Okay, so I did 0.75 is to 3 as x is to y. Remember what y is. It's that little height. It's this little edge here. I'm going to do a little circle on it and then I erase it. That's where y is. Okay, let me back that off. So there's the cross products are equal. 0.75, ooh, that's gross, equals 3x. And then if I divide, the thing is I need to replace this x with something in terms of y. So I'm going to divide both sides by 3. What I get is 0.25 y is x. That means wherever I see an x, I'm going to replace it with 0.25 y. So you want to see a brand new crazy picture? I got this trapezoid now that looks like this. I know it's 3 wide at the top, 1.5 at the bottom. I don't know if I can make it all fit. And I know that the middle width, see if you can follow me here, since I have x on either side and a 1.5 in the middle. And remember, I redefined x as 0.25 y. So what that means is that middle width is 1.5 plus, what is it, 0.25 x and a 0.25 x, which is ultimately a 0.5 x. That middle width that I've been dying to get is right there. It's 1.5 x plus, did I do x? That's y's. Yeah, we replaced the x's with y, so they're 0.25. So, right idea, wrong variable. There you go, y. 0.25 y. And remember what that came from is an x on either side, 0.25 y plus another 0.25 y is a 0.5 y that we see right there. Okay, so now we're ready to rock and roll. Take this thing to the next level. You okay with this? This is getting goofy. That's, you know what we just found? If you've forgotten, I would totally understand. But what we just found is the width of our one slice here. And if I take a look at this just right, if I go in here, I'm going to write it in the black. What I have is this width here is 1.5 plus 0.5 y. Okay, that's what's going on in that thing. So the volume of one of those pieces, that's what I've been needing all along. The volume of this thing right here is length times width times height, which is 10 times 1.5 plus 0.5 y dy. Okay. Yeah, buddy.
Can you go and go swimming?
Yeah, and if not yet. Don't get him up yet. Can you wait, please? Ethan, don't wake him up. Oh, good. Okay, so now what we've got, that's just the beginnings of it. All right, I haven't gotten to the physics part of it yet, and it only just begins. One of the key things about physics, and I don't know how much you guys have reviewed or you've seen in another class, but there is the idea of adding, to getting work. Work is the integral of force. And if you can get that piece down, so I'm going to take the integral of force, and if you remember, force is mass times acceleration. So what we're doing is I'm just writing a couple things, and let you just kind of roll with that for big ideas for just a second. Nope, you can use it, honey. And so that force equals work, integral of force equals work is a huge deal, because force is mass times acceleration. So if I erase that, yep, you just let it rip, buddy. It's fine. And so that's mass times acceleration. Okay, then go play. I'll take care of it. And so mass times acceleration is, and the mass of something is its volume, and times, okay, yeah, honey, times density.
Grandma said I can go stay with her.
Oh, cool. We'll do that. Yeah, that'd be fun.
I said Grandma.
Sounds good. And then volume times density will give you that mass. And we just found, and we went through all that work, hey, we found volume. Way to go. Hey, density was given to us. It's 1,000 kilograms per cubic meter for water. So we'll take our little volume formula times 1,000, and then acceleration for force is acceleration due to gravity, because we're just looking at, we need to lift this thing up, and the only thing that's working against it is acceleration due to gravity, and they hand that to us too. It's 9.8 meters per second squared. Whew, isn't that something? Okay. Now, you're going to pause and look at that. That's great. I'm going to erase it because I got to go back and draw in all the other stuff. We're going to put it all together in this one integral to get our work. Okay, I'm going to try and write small for first time through, and then I'll condense it a little bit. So, mass, the first thing was, remember, we took the mass we got from volume times density. So here's density. Here's our volume thing that we just came up with right below here, right? We're going to drop that in there. So here it is. Maybe I should write in green. Oh, my word. My children are having fun, but they're going crazy. Is the 10 times 1.5 plus 0.5y. Okay, there's that volume thing. Ooh, we don't want that. We want red, right? Go red and undo. There we go, red. And then, if you remember, there's a dy at the end of that. And don't forget that one other thing was times acceleration, because this is right here. That right there is just mass. And to get that, that's mass times acceleration, because we want that to be our full-on force. And acceleration was 9.8. Well, that's an easy one. We should multiply this times 9.8. There you go. Bingo. Now, both of those constants can be pulled out front. This is going to come out front. I mean, if you want to pull the 10 out with it, you sure can. But really, ultimately, what we want to do is that's going to be our nice little formula. It's going to be the integral of that thing. And if you can remember what the whole context was, if you look at this, let's go back to the original one. If I can zoom in just enough, maybe go green a little bit here, nicer green than that one. This right here, that's y, that little green thing that I put in there, so I'm going to draw an arrow over there and say y. And then the distance above that, I'm going to go on this nice, I forgot what color that's called. I'm going to go pink. This is 3 minus y. Okay, that's our depth piece right there. We know that those are our range of y's. It goes from the variable that we're dealing with, the integral is always in terms of dy. That means whatever you put here is going to be your minimum y that we're considering in this problem to our maximum y that we're considering in this problem. And since the way we've oriented this, this right here, the very bottom of the barrel, that's 0, 0. Okay, in the center. So our values, and the tank is 3 meters tall, so this is going to go from y equals 0 to 3. So there's your integral, and I think one of the problems asks you, hey, look, here's 9.8 times 1,000 out front. What do you want to put inside the rest of it? And then it asks for the upper and lower limit. Well, let me know if you can't interpret what I've written in there, but it's all in there, all the pieces you need right in here should allow you to answer that question right there. And the function that you're going to use for depth, of the water, and the width for the water should be the two things that I showed you. The only thing that I think my math lab, okay, I'm going to do a little more circling here in various colors. You know, here's the width formula. They might ask for it in a different way. If you put a 3, like multiplied 3 by 3 and then divided by 2, that could be 3, or what would it be? I don't know, you could do a couple of things that make this better. Multiply it by 2. 3 plus y over 2 is another way to write that one. So 3 plus y over 2 is another way of writing 1.5 plus 0.5y. It may want you to write it in a different form, so who knows. What function y will you use for depth? Remember when we did this 3 minus y thing way down here at the bottom? It's going to go up there. I'm thinking it's 3 minus y is the depth that you're needing, but it might be y. Y or 3 minus y, one of those two. Let me know how it goes, and then we can go from there. That should get you through that problem. Let's roll with that and then just get back to me. All right.